In this section, we're going to begin looking at comparisons between two population parameters. Specifically, in this section, we're going to do inferences on two population proportions. So in other words, we're going to be comparing whether we think that two population proportions are equal to each other, not equal to each other, one is larger or smaller than the other. Before we can do that, however, we need to determine whether we have sampling methods that are independent or dependent. So we have definition. A sampling method is independent when an individual selected from one sample does not dictate which individual is to be in the second sample. A sampling method is dependent when an individual selected to be in one sample is used to determine the individual in the second sample. Dependent samples are often referred to as matched pairs samples. It is possible for an individual to be matched against him or herself. So let's begin by looking at an example. Determine whether the sampling is dependent or independent. A researcher wishes to determine the effects of alcohol on people's reaction time to a stimulus. She randomly divides 100 people aged 21 or older into two groups. Group 1 is asked to drink 3 ounces of alcohol, while Group 2 drinks a placebo. Both drinks taste the same, so the individuals in the study do not know which group they belong to. 30 minutes after consuming the drink, the subjects in each group perform a series of tests meant to measure reaction time. So again, we want to determine if our sampling method is dependent or independent for Part A. So in Part A, because the individuals in the second sample are not dictated by the individuals in the first sample, in other words, the individuals in Group 2 are not determined by the individuals in Group 1, or vice versa for that matter, we have an independent method. So the answer to Part A is that the sampling method is independent. Let's look at Part B. A researcher wants to determine the effect of color on people's reaction time to a stimulus. She obtains a random sample of 250 people and measures each person's reaction times to a fluorescent orange stimulus and to a fluorescent green stimulus, order of color rotated. So in this case, the first group and the second group, those whose reaction times are being measured for the fluorescent orange stimulus and those whose reaction times are being measured for the fluorescent green stimulus, are the same individuals. So this is a matched pairs design. So because of that, this sampling method is dependent. So the sampling distribution of the difference between two proportions if we have independent samples. So for the remaining of this section, we're going to be looking at two proportions and we're going to be dealing with independent samples. Suppose a simple random sample of size N1 is taken from a population where X1 of the individuals have a specified characteristic, and a simple random sample of size N2 is independently taken from a different population where X2 of the individuals have a specified characteristic. The sampling distribution of p hat 1 minus p hat 2, where p hat 1 equals x1 over n1 and p hat 2 equals x2 over n2, is approximately normal, with mean mu sub p hat 1 minus p hat 2 equals p1 minus p2, and standard deviation sigma sub p hat 1 minus p hat 2 equals the square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2, provided that n1 times p hat 1 times 1 minus p hat 1 is greater than or equal to 10, and n2 times p hat 2 times 1 minus p hat 2 is greater than or equal to 10, and each sample size is no more than 5% of the population size. The standardized version of p hat 1 minus p hat 2 is then written as z equals p hat 1 minus p hat 2 minus the quantity p1 minus p2 all over the square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2, which is an approximate standard normal distribution. So the point here is that as long as our conditions are met, as long as n1 times p hat 1 times 1 minus p hat 1 is greater than or equal to 10, and as long as n2 times p hat 2 times 1 minus p hat 2 is greater than or equal to 10, and as long as we have independence within each sample, so again the sample size can't be more than 5% of the population size for either sample, as long as those conditions are met, then the sampling distribution of p hat 1 minus p hat 2 will be approximately normal, and the mean of that p hat 1 minus p hat 2 distribution will be p1 minus p2, and the standard deviation of that p hat 1 minus p hat 2 distribution will be the square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. So that's the significance of this. We will have a normal distribution approximately, as long as these conditions are met, for this sampling distribution of p hat 1 minus p hat 2. So this is a new type of sampling distribution that we're going to be dealing with that's going to allow us to be able to do inferences, meaning we'll be able to do both hypothesis tests and confidence intervals when we're dealing with two proportions, again, as long as they are independent samples. So what we're going to be doing, we're going to be conducting a hypothesis test where we can determine whether the two population proportions are equal or not. So the structure is going to be this. We're going to have a null hypothesis that's going to say that the proportion from population 1 equals the proportion from population 2 versus one of three alternative hypotheses. So the alternative hypotheses will either be that P1 does not equal P2, the proportion in population 1 does not equal the proportion in population 2, or P1 is less than P2, or P1 is greater than P2. So the alternative hypothesis will be one of these three things. If we have not equals to, that will lead to a two-tailed test. If we have less than, that will lead to a left-tailed test. If we have greater than, that will lead to a right-tailed test. So we'll have one of these three structures, but in order to be able to do this, we have to have a distribution of the differences in the sample proportions that follow a normal distribution. So that's what we're going to be looking at now. If we have P1 equals P2, that is equivalent to saying that P1 minus P2 is equal to 0. So our textbook looks at it this way, but other resources will look at it this way. So we need to be familiar with both. For example, we'll see that StatCrunch looks at it this way. If P1 is not equal to P2, that is equivalent to saying that P1 minus P2 is not equal to 0. If P1 is less than P2, that is equivalent to saying P1 minus P2 is less than 0. And if P1 is greater than P2, that is equivalent to saying P1 minus P2 is greater than 0. So again, our text is going to use this approach, but other resources may use this approach, looking at the differences in the proportions and comparing those to 0. Now, in order to be able to conduct this hypothesis test, we need to have a normal distribution for the sampling distribution in the differences of p hat. And so that's what we're going to look at next. So when we conduct a hypothesis tests always work essentially the same way. We will use the same techniques that we learned in the previous chapters, both for hypothesis tests and for confidence intervals. So if we're dealing with a hypothesis test, then we will have the classical approach that we can use. We will have the p-value approach that we can use. And if we have a two-tailed test, then we will have the confidence interval approach that we can use as well. So this is looking at the test statistic that we would obtain. So if we take p hat 1 minus p hat 2, that would be our results. So we're going to be taking the proportion of individuals in the first sample that have the characteristic minus the proportion of individuals in the second sample that have the characteristic. So we're finding the difference between the two sample proportions. And that minus the difference between the two true proportions, p1 minus p2, divided by this standard deviation, which again is the square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. That's going to be our test statistic. But we can simplify that. As a general rule, we're going to assume that the two population proportions are equal to each other until evidence convinces us otherwise. So if P1 and P2 are equal to each other, then P1 minus P2 would equal 0. So that's where this is coming from. So if P1 minus P2 equals 0, then we'll just be left with P hat 1 minus P hat 2, okay, which is where this is coming from. Now, if P1 and P2 are equal to each other, then we'll just call those generically P. So if P1 equals P and if P2 equals P, then we could replace the P1 and the P2s with just P here. So that's what's being done here. So we have P times 1 minus P over N1 plus P times 1 minus P over N2. And then we can factor out the square root of P times 1 minus P, and that's what's done here. So we have the square root of P times 1 minus P times the square root of 1 over N1 plus 1 over N2. Again, we're just factoring out the square root of P times 1 minus P. Now again, I'm showing you this because this is going to be the test statistic that we're going to see shortly. Now, because P is unknown, we're going to have to estimate it. Just like we did in the previous chapter, we don't really know what P is, so we're going to use P hat as an estimate. So for our estimate for P in this calculation, we're going to use what is called the pooled estimate. And the pooled estimate, P hat, is going to equal x1 plus x2 over n1 plus n2. So we're going to pick up in a new video and we're going to walk through a hypothesis test regarding the difference between two population proportions.